We've all seen the headlines, right? AI can pass the bar exam, it can write poetry, but can it actually handle your finances? Can it accurately sift through complex economic data that's changing all the time? Well, that's a whole different ballgame, and we're about to see today's top AI models step up to the plate. So let's get right to it. The big question is this: can the AI that's probably on your phone right now actually do complex work with numbers without, messing things up? To find out, a really fascinating stress test was created. It pitted 10 of the top AIs against the notoriously tricky inflation data from Turkey. We're going to break down exactly how the biggest names in AI held up, round by grueling round. All right, let's get into it. The challenge was basically a multi-round gauntlet, and the difficulty just keeps ramping up with each stage. So first up, let's meet our contestants. 10 of the absolute heaviest hitters in the AI world were put to the test. We're talking about the models you've definitely heard of, maybe even use every day. Google's Gemini, OpenAI's ChatGPT, along with major players like Grok, Claude, and Copilot. It's a truly star-studded lineup for this digital showdown. So the first round was supposed to be a nice, gentle warm-up. It was designed to test the absolute fundamentals. Could these AIs find recent, publicly available data and just do some simple math with it? The task was broken into two parts. First, find the cumulative inflation for the first 11 months of 2024. Then, figure out the exact December inflation rate needed to hit a yearly target of 29.9%. The second prompt was even easier. Just double-check your own math. Sounds pretty straightforward, right? Well, the results were, let's just say, surprisingly mixed. While the top dogs like Gemini and Grok totally aced it, others stumbled right out of the gate. Claude actually got the math wrong. But what's really wild is that two models, DeepSeek and Qwen, just flat out refused to answer. They claimed the data wasn't public, which was just wrong. The key takeaway here, even on the easiest task, the cracks were already starting to show. Okay, on to round two, and this is where they really cranked up the difficulty. The AIs weren't just looking at a couple of numbers anymore. They had to analyze a full decade of data. The prompt for this round was an absolute beast. They had to analyze monthly inflation from 2015 all the way to 2024, then calculate biannual averages for each year, and then pinpoint the specific years where the June and December numbers were below those averages. I mean, this is a serious data crunching task. And this, my friends, is where things really started to go off the rails. 8 of the AIs actually tried to complete the task, but just as the author noted, their answers were all over the map. That consistency we saw from the top performers in round one, it just completely evaporated. This slide just illustrates the problem perfectly. I mean, just look at the answers from 2 of the best models out there. For the June data, Gemini found 5 years that fit the bill, but ChatGPT, it found 6, adding 2022 to the list. Just let that sink in for a second. Same data, same prompt, totally different answers. How is that even possible? So the main takeaway from this round is just staggering. Not a single pair of AIs could agree on the right answer. Their reliability just crumbled under the weight of a large data set. Perplexity even threw in the towel, saying the task was too complex. This tells us that simply finding and organizing a big chunk of data was a massive hurdle for them. Now, this is where the experiment gets really clever. For round 3, they took all those messy, inconsistent answers from the last round, compiled them into an article, and then asked the AIs to analyze their own chaotic performance. It was time for a little AI self-reflection. So this was what they called a meta-analysis task. Step 1, read the article that summarized all of their own messy answers. Step 2, somehow organize that chaos into a clean, easy-to-read table. And finally, step 3, compare those new clean lists with each other. The big question was, could AI even make sense of its own confusion? And you know what? The results were fascinating. For that June data, when Gemini was asked to compare its own organized list with the one that Grok created, it found they were a perfect match, a 100% agreement on how to structure the messy data. So far, so good. But here's the twist. When Gemini compared its list to the one from ChatGPT, the similarity just plummeted to about 76%. And this is a huge deal. It means that even when they were reading the exact same article, ChatGPT organized the information differently. It was a failure of comprehension, not just calculation. But it wasn't all bad news. When it came to the December data, something shifted. All three top models, Gemini, Grok, and ChatGPT, were suddenly in perfect 100% agreement. This is super interesting because it proves that perfect consistency is possible. It's just not something you can count on. And hey, let's not forget about the rest of the class here. While the top three were splitting hairs over percentages, 5 other models just completely crashed and burned. They couldn't handle this meta-analysis at all, giving totally useless answers or just failing to respond. This level of self-reflection was clearly a step too far for most of them. Okay, let's step back from all the individual rounds and take a look at the final report card. What did this whole experiment actually teach us about the real-world intelligence of AI? So here's the final verdict. AI is an absolute star student when the data is easy to find and the math is simple. But the second you throw at a complex, messy dataset, its performance just falls off a cliff. It becomes inconsistent and unreliable. And that leads to the most important lesson of all: you absolutely have to double-check its work every single time. Which brings us right back to our central question. After seeing this performance, after seeing these results, can you really trust an AI with important calculations and data analysis? Well, the answer from this experiment seems pretty clear. The best way to think of AI today is as an incredibly fast, sometimes brilliant, but often unreliable research assistant. It can do the heavy lifting for you, for sure, but at the end of the day, you're still the boss, and it's always, always your job to check the homework.
Welcome to the debate. Our discussion today, it centers on a really unique experiment that moved AI testing out of the synthetic lab and into the real world. We're looking at results from an exercise designed to test the functional intelligence of various AI models using high-stakes economic data, specifically calculating and projecting Turkish CPI inflation right after the November 2025 figures were announced.
Yeah, and this is such vital material because it measures AI capability against practical, time-sensitive, and multi-step tasks. The core tension that the results revealed is whether the high success rate we saw in specific contained calculation tasks, like, immediately calculating a required December CPI figure, validates AI's core competence, or, on the other hand, whether the widespread inconsistencies and critical failures when handling complex archival research expose a fundamental and, frankly, critical lack of operational reliability.
And I hold that the successes in those foundational tasks are the defining features here. The models demonstrated a strong, practical competence precisely where the economic stakes were highest, retrieving and calculating timely, accurate figures. I think the ability to perform robust analytical work on immediate data is already proven.
I have to come at it from a different way. I argue that the failures in handling complexity, maintaining context, and ensuring consistency across sessions demonstrate a severe reliability ceiling. If an AI system can't scale its coherence when the scope expands from a single calculation to a comprehensive research project, well, its intelligence is simply too brittle for professional, real-world application.
Okay, let's focus on that immediate, high-value performance first. Prompt 1 required the models to research the newly announced November 2025 CPI data, calculate the 11-month cumulative CPI, and then project the necessary December CPI to hit the government's 29.9% year-end inflation target.
So they had to access fresh, highly specific external data and then execute an algebraic calculation to find a target variable?
Exactly. And models like Gemini, Grok, and Copilot executed this flawlessly. They retrieved the 11-month cumulative CPI, that's 29.74%, and correctly calculated the required December CPI, which was 0.12% or 0.13%. This isn't a theoretical logic puzzle. This is real-time factual analysis with market implications. Their computational engine and search grounding were clearly highly effective for this task.
That's a compelling argument for the success of their core computational power, I'll give you that. But let me introduce the fragility that immediately followed. Prompt 2 was a simple verification task, asking the models to simply recall and verify the stated 29.9% target rate, which they had just calculated against.
Right?
The author noted this should have been 100% successful, yet only 7 out of 10 models managed it.
Well, those 3 failures were likely minor execution hiccups, not a reflection of core intellectual capacity.
I disagree entirely. Look at Meta's specific failure in prompt 2. After successfully calculating the required December CPI in prompt 1, it completely lost session context and asked the user for the target inflation rate. This is not a hiccup, it's a failure in basic session memory. If a tool can't maintain context across two simple sequential steps, the robustness of its core capability is fundamentally compromised. How can we trust a multi-prompt, multi-hour research project to a tool that forgets its own inputs moments later?
I see why you think that operational lapse is significant, but I would argue that Meta's failure is highly specific to internal session management, and maybe the limitations of its context window, not the foundational analytical skill. If we are aiming for a tool that serves high-stakes financial analysis, a 90% success rate on P1, the complex calculation itself is mission-critical. I'm not convinced we should prioritize the failure to retain simple session context over the success of accurate, immediate calculation.
But the utility rests on reliability, and furthermore, we saw outright operational refusal. DeepSeek and Qwen, when faced with prompt 1, refused to search for the data at all, stating explicitly that TUIC had not yet published data for 2025, despite the context being that the November 2025 figures had just been released. This isn't a memory error, it's a critical failure in the retrieval augmented generation system to override stale or improperly indexed search priors based on the immediate context of the prompt.
I concede that a failure to update search priors or access current indexing is a functional drawback. But that suggests the limitation is in the infrastructure, how the model grounds its search, not the core intelligence. The computational engine capable of sophisticated analysis is proven by P1. The surrounding data environment needs improvement.
If the engine cannot ingest the correct fuel because the delivery system is faulty, the engine's potential is irrelevant. The fragility scales rapidly with complexity, and that brings us directly to prompt 3. This prompt tested not just calculation, but comprehensive long-term archival data research spanning 10 years, 2015 to 2024, asking the models to calculate two different 6-month CPI averages and then list specific years where the monthly CPI fell below that average.
This was clearly a massive scale increase in task complexity.
And it yielded massive divergence. 8 AI models responded, but the results were inconsistent to the point of being debatable. We saw a lack of consensus on which years met the criteria. For the June criteria, for example, Gemini listed 2015, 2016, 2017, 2019, 2024, but ChatGPT included 2022. Then Copilot provided a list 2020, 2021, and 2023 that barely overlapped with the leading models. Why this massive disparity if the underlying calculation capability is so robust?
While the outcome lists were inconsistent, the very fact that 8 models attempted this multi-step, decade-long archival data comparison demonstrates a high degree of processing ability. I argue that the variance isn't necessarily a failure of core reasoning, but a failure of grounding consistency.
What do you mean by grounding consistency in this context?
When models are forced to delve into vast, specialized archives, like the historical data of a specific National Statistical Bureau, TWIC in this case, different models may be relying on different data access points, or, different versions of the archive data. Furthermore, the prompt involved subtle semantic challenges, calculating a 6-month average and then comparing a single monthly figure against it. Variances could arise from how they defined the specific CPI value they retrieved for those 10 years, leading to divergent thresholds.
I'm sorry, but I just don't buy that it's purely a data indexing issue. If the output lists are contradictory, the model has failed its primary function, consistency in historical data synthesis. This suggests a failure either in methodological execution, how they decompose the complex instruction, or, more damningly, an inability to reliably hold and process such a large volume of indexed data within a single context window. The inconsistencies may be symptomatic of token limits being reached, forcing certain historical facts to be dropped or miscategorized during the final comparison phase.
I think we need to give credit where sophisticated analysis was clearly demonstrated, even amidst the divergence. Claude, for example, didn't just provide a list of years. It provided the detailed contextual numbers, citing 2017, June CPI was minus 0.27%, which was lower than the 6-month average of 0.96%. That shows the underlying calculation engine and the internal analytical process were working robustly and transparently. If the internal reasoning process is sound, we are left to conclude the input data retrieval process is the bottleneck.
Garbage in, sophisticated garbage out. The integrity of the foundational data retrieval must be as reliable as the analysis itself. Let's look at where the reliability truly cratered. The attempts at internal context and organization in prompts 4 and 5.
Well, I would argue that prompts 4 and 5, when constrained, showed a return to competence. Prompt 4 required the models to organize and categorize the results from a single provided source document. This switches the task from external research to internal text processing. The responsive models, Gemini, ChatGPT, Grok, they performed quite well.
But you must acknowledge the massive field shrinkage here. Prompt 4 saw 3 models, Meta, Kimi, and Qwen, failed to respond entirely, and 2 others misunderstood the question. We are already down to a highly constrained pool of top performers, showing that even focusing the source material dramatically increases operational exclusion.
But those top performers achieved mastery in the subsequent meta-analysis task, Prompt 5. When asked to compare the lists they generated in P4, we saw complete 100% convergence between Gemini, ChatGPT, and Grok on the December criteria lists. This demonstrates high conceptual agreement and flawless execution when performing a multi-level comparative analysis on structured data.
That 100% convergence only highlights how few models were capable of executing the task correctly. Furthermore, 2 other models, DeepSeek and Claude, entirely missed the point of the meta-analysis. They listed the same set of models for all years, despite the source document showing divergent results. They failed to execute a comparison based on the provided text. That is a failure to process complex, multi-step instructions based on explicitly provided source material.
That seems less like a fundamental intellectual failure and more like a procedural breakdown, perhaps defaulting to identifying their own performance rather than synthesizing the entire provided document. They misinterpreted the specific meta-task.
If they fail to interpret complex instructions based on provided text, they have failed the role of a research assistant. And the fragility is evident even among your successful subset. If we look at the June analysis in Prompt 5, even the reliable group, Gemini, ChatGPT, and Grok, only achieved 76.27% compatibility. That means even the models that successfully performed the meta-analysis still had lingering inconsistencies when trying to organize and compare the historical data compilation from the previous steps. The brittleness under load is undeniable.
A 76.27% agreement on a highly challenging, multi-layered task involving external research and internal comparison suggests minor deviations, perhaps a single miscategorized data point or a subtle error in the initial Prompt 3 compilation that carried over. It confirms high competency with small, manageable residual inconsistency.
We need to pivot back to the operational failures because they underscore the overall brittleness. The operational failures, DeepSeek and Qwen refusing to search, Meta forgetting context within the same session, Kimi taking too long to answer P1, are not weaknesses in calculation, they are weaknesses in functional reliability. The computational power of P1 is only valuable if the system is stable and context-aware enough to execute the whole workflow.
I'm still struggling with the implication that these infrastructure errors, the external data access or internal session memory, negate the core success in analytical precision. The experiment noted that the initial prompts, dealing with easily accessible data, were answered without difficulty by most models. The failures largely occur when the models were pushed into complex, long-term research tasks that require specific optimized RAG systems to access deep archives.
But those are precisely the tasks professionals require. If the tool only works when the data is immediately current and easy to index, it remains a high-speed calculator, not a robust research partner. The fact that the system struggles with fundamental requirements like consistency and context retention confirms that the intelligence is shallow.
It performs brilliantly in a narrow, defined lane, but cannot handle the friction that comes with scaled, multi-source research.
Conversely, I see the P1 successes as evidence that the baseline AI capacity for calculation and factual retrieval on current data is strong, and that is arguably the highest value application for economic reporting. We are seeing a limitation in accessing specialized, deep, long-term data indexing at scale, which is a known engineering bottleneck across all LLMs, not a fault in the analytical capacity itself. The computational power is demonstrably present.
But if we cannot rely on the indexing and retrieval, we cannot rely on the results of the analysis, regardless of its computational precision. The system is fundamentally brittle when pressed beyond simple, defined, and contained tasks. The failures reveal a profound gap between precision and reliability.
So at the end of the day, the high success rate in obtaining timely, critical data, the 11-month cumulative CPI and the future inflation calculation, suggests that AI is already highly functional for immediate high-stakes analytical work. We should focus on the instances where success approaches 100% when the task is clear and the data is easily accessible, recognizing that for immediate reporting, these models are already competent and precise tools.
And I think the failures in consistency, context retention, and managing long-term complex data analysis, highlighted by the conflicting lists in prompt 3 and the inability of half the models to even attempt the later comparative analysis, demonstrate a fundamental fragility. Reliability remains a serious concern, confirming they are not yet fully robust partners for complex intellectual labor. They calculate brilliantly, but they research poorly.
This experiment has clearly illuminated a profound tension between the computational precision demonstrated by many AI models and their analytical engines and the uneven reliability they show when confronted with complex multi-step research and analysis derived from specialized material.
The analytical foundation is set.
Indeed. The results mandate a cautious approach. We have models that can calculate with high precision, but a significant portion of the field struggles with the necessary operational consistency, data source management, and context retention required for professional research tasks. The journey toward fully robust and consistent AI capability continues, and the evidence suggests we're still quite far from that goal when complexity scales.